Welcome to the next class. What we're going to be doing today is talking about the active object pattern and relating that to the various mechanisms at work in Android. So what we're going to do first is we're going to talk about what the active object pattern is and how it's used to structure the solution for concurrent software. And then we're going to talk about how the active object pattern can be applied in Android. And I'll give you a bunch of different examples from some things we've already seen to some extent, but we're going to look at them a little bit differently now in the context of patterns. And we're going to be doing this, of course, throughout the course. I'll be talking about how Android works. We'll be talking about the classes. We'll be talking about the interactions between the classes. We'll be talking about frameworks. And then I'll always try, whenever it makes sense, to relate the design choices that Android makes back to patterns. And the benefit of doing that, of course, is not only do you perhaps understand how Android works a little better, because you can connect it to other written literature that talks about the solution in a perhaps more abstract way than Android documentation does. But even more importantly, you'll understand how to solve similar problems. So even if you're not programming in Android, if you're programming in some other software environment, but you run across the same kind of forces that Android ran across, you can know what patterns to apply to your solution. So it's meant to give you both something very specific and also something more general. And it's worth pointing out that's one of the beautiful things about patterns. They help give you immediate benefits, and they also give you something that will be fundamental and will last for decades. Many of the patterns we cover here have been known for 20 or 30 years by some people, and the goal, of course, is to make sure that you guys know them as well. All right, so the particular context we're going to focus on here is a situation where a client wants to invoke methods of an object that's running in another thread of control, or it wants those methods to run in another thread of control. Now, this, of course, is a generic issue. We're going to talk about it primarily in the context of Android, but as we go through the pattern, you'll see that the topics are much more generalized than just Android. In this particular context, a client is any Android code, an activity, a service, or whatever, that wants to execute a method. So client, sometimes we think of clients as being the hardware that is used to connect to servers. And that's one way to look at it, but a more general way to look at it is client is just whoever's invoking an operation at any given point in time. So for example, we might have a situation where some background thread wants to be able to invoke an operation like, say, send message and pass a message to a handler that's actually connected to another thread of control. So that would be the context for this particular discussion. So you can see here we have a background thread, and it says handler.sendMessage. The handler, of course, is associated with this UI thread, and the handle message method gets called back, and it does something or other that was requested or passed by the client, by the caller, which was a background thread. More generally, of course, we can have the threads be any threads. They don't have to be a background thread and a UI thread. That's one common use case. But in Android, of course, and more generally, you can have any threads that are running, and they want to invoke objects whose implementations reside in or want to execute in another thread of control. So we can generalize this point. Same pattern applies, same structure applies, just a slightly different way of looking at it, slightly different mapping onto mechanisms and use cases in Android or some other system. So some of the problems or the design forces that we're trying to address here, we'd like to be able to leverage the available parallelism on the platform as transparently as possible. We really don't want to require application developers to have to know a lot about locking and synchronization. Much the same sort of argument we thought about when we discussed the monitor object pattern, but there's a little bit more to it here. Remember when we talked about monitor object, what was the defining characteristic of an invocation on a monitor object? What's the main thing to think about in that context? Who ends up running that invocation? When you call a method on a monitor object, when you call a synchronized method on a monitor object, who ends up running that method? You being the client
thread.
Yeah. So the client thread is what ends up invoking it. So basically, in a monitor object environment, as with a normal object, you invoke a method on the object, and the callee, the guy who's called, steals the thread of control of the caller, and it runs in that context. Another thing we want to be able to do is ensure that if you have long-running operations, that they don't block other things in the process from executing. This is primarily relevant if you're trying to run things in the UI thread or in a single thread solution, and any one thread of control, if it were to block, would cause the whole process to hang. And we don't want that to happen. That's another problem we want to avoid here. And then the last piece of the puzzle here is we want to make access to these shared objects and synchronized objects as simple and as intuitive as possible. We don't want people to have to know about the low-level details of conditions, monitors, queues, all that kind of stuff. They just want to make a method call, and magic happens, and that method is executing in another thread of control. So to do this, we're going to apply the active object pattern. The active object pattern is a pattern that's documented in the POSIT 2 book, and it's actually, as you'll see later when we talk about known uses, it's actually a very widely used pattern. There's actor languages, there are actor libraries, there's all kinds of things that implement this particular model. And we use it to decouple the thread that invokes a method from the thread that runs the method. So we're going to decouple method invocation from method execution. And method invocation occurs in the client thread, the caller thread, and method execution occurs in some other thread. However, from a client's point of view, this should look like just a regular method invocation. It doesn't look like you're doing anything special. You're not treating the data or the invocations in any special way. You're just invoking a method, and voila, something magic happens, and the work gets processed in another thread of control. In particular, the client doesn't grab any locks, it doesn't use condition variables, it doesn't do any queuing, it just says, send message or invoke operation or something like that. So the active object pattern, the intent of the active object pattern is to define service requests on components or objects and make these be the unit of concurrency in the program, and then run requests for these services in different thread or threads than the requesting client, and then be able to enable the client and the component to interact asynchronously to produce and consume results that occur as a result of invoking the service. Now, that may seem like a bit of a mouthful, but it's actually very, very straightforward, and we'll talk about each of those steps, each of the pieces of the intent as we walk through this. In a nutshell, if you look at this picture here, what's happening is we have a client with a client thread invoking some method on some interface, and some magic happens, and then this thing gets turned into some kind of so-called objectified service request, which is a linearization of the parameters and the information that corresponds to the method call. And that thing then gets stuck into some kind of activation list or queue that is managed by the active object. And that guy runs in a separate thread or threads of control. And when the request comes in, it gets stuck in the queue. And then at some point, a scheduler takes the request out of the queue and invokes an operation back on some servant, which is the implementer or the executor of the original invocation by the client. So that's how the service request gets invoked in the active object thread or threads. Yeah, Sean.
In the diagram, you're calling method 1, but method 2 is eventually getting called. Is that?
Oh, that's a good point. It should be method 1 getting called. Okay. That's a really good point. I have to fix that. That's actually a typo from somewhere else that I got to fix. There's a paper that talks more about this that's on my website. You can also take a look, of course, at the POSIT 2 book, which is where the full-blown pattern is described. Okay, so when would you want to apply this pattern? What would be the circumstances under which this pattern would make sense? Well, one circumstance would be when you want the methods of an object's interface to define its concurrency boundaries. So much like with monitor object, when you make a method call, you want that thing to be the place where the boundary of concurrency is going to be managed. You don't want people to have to acquire and release locks explicitly, for example. You should also do this when you want the object to be able to do all the work internally and not make the client responsible for any of the work. And you also do this if the methods that you call may need to block. Maybe they have to download a big file, or they have to grab a lock, or they have to do some long-running computation that won't return right away. So those are sort of 3 factors that are important to consider when you want to apply this pattern. Then some other things that are important when you want to be able to have multiple client method requests running concurrently on a single object. Now this is different from the monitor object. The monitor object only lets one method run at a time. It locks out anybody who's not that one method. With Active object, however, in some configurations, you can actually have multiple method requests running simultaneously, subject to various synchronization constraints or scheduling constraints. We'll talk more about that. And another thing you might want to have here is you might want to be able to allow the invocation order to differ from the execution order. So the order in which you invoke the operations may not be the same as the order in which the operations are actually run. And again, this has to do with scheduling constraints. It has to do with timing properties, priorities, and so on and so forth. So we'll come back and talk a bit about that. Now, what's important to note here, and we'll come back and look at this a couple different times, is to compare and contrast active object with monitor object. Some things are very similar. The stuff in green here are essentially the same motivations for why you might choose to use monitor object. You don't want clients to really know that synchronization is taking place explicitly. It's implicit in the framework or in the implementation. You would like to be able to have the method call interface be the boundary for concurrency, and you want to be able to allow things to block without causing problems. To some extent, monitor object can still get you into trouble if you block, so you have to be careful there. In fact, I'll tell you what, because this is important, let's gray that one out. That's really not a good reason. So it's those two reasons. And then the other ones are ones where active object has additional capability. It allows things to run concurrently. It allows things to block without disrupting other threads and other behaviors. And it allows the execution order to differ in a wider variety of ways. And we'll talk more about active object and monitor object. A good quiz question at some point will be compare and contrast active object and monitor object. So make sure you understand these things for the quiz. But of course, much more importantly, make sure you understand the differences, because they're important differences to understand from a conceptual and practical point of view. All right, so here's the structure of the active object pattern. As you can see, there's a lot of moving parts that are going on here. And so we're going to step through them one at a time. Now, when I show you the example, I'm going to do this in two ways. I'm first going to explain it, well, actually, I'll tell you what. First, I'll explain it in terms of everyday experiences you may have had at some point along the way. And then I'll talk technically about what's going on. And so this may help you to understand things better. So I'll kind of go through this with a metaphor. So the metaphor is you're going to a fast food restaurant in order to get lunch or get food. Now, as you all know, there's different kinds of fast food restaurants. There's the McDonald's style of fast food restaurants where, at least historically, they've changed a bit over time, but historically you went to McDonald's. The goal of any fast food restaurant is to get people to pay and out of the way as quickly as possible, right? It's about throughput, because that equals cash flow equals profitability, which all entrepreneurs like, right? And so what we want to be able to do is find a way to maximize throughput. So if you go to McDonald's and you order a Big Mac, fries, and a Coke, at least in the early days, what they would do is they would pre-cook a bunch of things. They'd have a bunch of pre-cooked French fries, and they would be under a heat lamp. They'd have a bunch of pre-cooked Big Macs under a heat lamp. They might even have had some pre-poured Cokes that were sitting there on the counter. And so when you say, Big Mac, fries, and a Coke, the cashier just sits there, reaches back, grabs the stuff that's been pre-cached, right? It's a good optimization technique, pre-caching, and gives you the stuff right back. And typically that's a synchronous transaction. You stand there, you order the food, as long as it's in the cache, you get it, you go on your way, they get their money, you get a heart attack or high cholesterol. And Christoph, now I'm going to get sued by the food lobby for food libel. Anyway, bad things happen, right? But they got the money and everybody's happy. So that's one model. That's not the active object. We'll talk about that later. That's called synchronous two-way blocking. That's kind of like the monitor object, actually. You can imagine you might have a monitor to make sure that two cashiers aren't trying to grab a Big Mac at the same time, or whatever. So the active object is different. In the active object model, let's use a different kind of restaurant. Let's talk about Wendy's. So does anybody know what's the big differentiator that Wendy's has compared to, say, McDonald's?
They don't pre-cook their stuff.
Cook to order. It's on demand, right? So imagine what would happen if they did Wendy's like they did McDonald's. You'd go up, you'd place your order for a double Wendy's, cheeseburger or something like that, and then they would go cook it for you on demand. Well, it would take forever, right? You'd be stuck there synchronously in that transaction space. It would take a long time, and people would get upset. Everybody behind you in line would get upset. The owner of the Wendy's franchise would get upset. Everybody would be upset, right? Because they weren't getting throughput, you weren't getting served. So what do they do instead? When you show up there, you have this transaction with the cashier. And the cashier plays the role of the proxy. So the proxy is sort of the one who's going to take your order. It's the ambassador or a surrogate for something that's actually going to do the real work. And when you place your order, you say, I want to have, this special burger with all the fixins or something. Then what they do is they turn around and they convert that into some kind of future, right? The future is the little plastic token they give you with a number on it. That's the future. They hand you something. And then they turn around, and you don't really see this anymore because it's all done through computer, but that turns out to be a method request or a message that shows up in the cook's message queue or message list, right, of things to cook. And so there's a queue of those things. Who knows how they're ordered? Let's probably assume they're FIFO order, but they could be ordered some other way. If let's see, try to think if Bill Clinton liked to eat fast food, right? So if Bill Clinton comes in, chances are his order is going to get moved to the front of the queue. So you might rearrange the order of these things based on the importance of whoever's making the order. So the requests are in the queue, and then the scheduler, which in this case would be the cook, would take the requests off one at a time, take a look at what they were, and then would start to cook the meal. And when the meal is done, then they need to deliver it back to the recipient, which is so cooking the meal is done by the cook when it comes to them from the scheduler. It says, okay, this is what I want you to cook now. So the cook meal is the operation on the servant. And when you're all done, you then have to give this back to the person who placed the order. And there's a couple ways to do this. And the way to do it is essentially to pass this information back to the caller through the future. And as you all know, in a fast food restaurant like Wendy's, there's two ways to do this. One way is to have you periodically go up to the pickup window with your little plastic token in hand, your future, and say, is item number 42 ready yet? That's called polling. So you poll for your result. The other approach is for you to go sit there and read a paper, browse the web, talk to your friends, whatever you do, make a phone call. And then when it's done, the person, the runner, or the cook or somebody will come out and deliver the food to your table. That's the callback model. So there's a polling model and a callback model. Now, of course, you could just stand there by the pickup window, just like a hungry puppy, waiting for the food to show up. That's possible. That's sort of a blocking future transaction. But that's probably not the best way to spend your time. And by the way, the other thing that they do in these restaurants, another form of optimization, is they have customers do some of the work, right? So they don't fill your cup for you. They give you a cup, and then you go and fill up your cup, right? And sort of the way it works is, the way they price the drinks, you'd have to drink like 10 gallons worth of soda to make up the difference in what you just paid for that soda, right? Because it probably cost them 10 cents and you paid $1.50 for the thing. So you'd have to drink a lot of stuff before you'd make up the difference. So anyway, that's the active object pattern described through a fast food metaphor. And then we also talked about the various elements, and we'll talk about them again in a more technical way next. Okay, any questions? So that's kind of thing. The other thing that I didn't really explain as I was talking about this is the mapping onto Android. So you invoke an operation on a handler, which is a proxy-like thing. And there's another way to use a handler as a future. We'll talk about that when we talk later. The method request in Android out of the box is essentially a message. That gets stuck into a message queue, which is the activation list. There's something we've seen before called the looper, which plays the role of the scheduler in conjunction with the message queue. And then whatever handler you define that subclasses from the default handler class and fills in the handle message method, that's the servant. And of course, the client is whoever invoked this thing in the first place, which is like some activity, perhaps. OK, so that's the static view. There's also, of course, a dynamic view, which isn't much different from what I just told you, because we spent a lot of time talking about the metaphor. So the client invokes a method call on a proxy, and the proxy converts the method call into a method request or a message, passes that to the scheduler, and returns a future to the client. The scheduler sticks the method request onto some kind of activation list or queue. At some point later, based on various properties, the scheduler takes the message off the queue and then goes ahead and dispatches it on the servant. Oops, that should be pointing over here. So the servant is the guy that actually does the work. And when he is done, then the client gets the results, either by polling or by some kind of callback. Okay, so that's basically the steps involved from dynamics in the active object pattern. Okay, so let's talk about what you need to do to implement this pattern. Now, I'm going to talk about the implementation in general, and then I'm also going to show you ways you could implement this in Android. Keep in mind that Android, the things we're talking about in Android don't implement the full-blown active object pattern. If you want the full-blown active object pattern, you'd have to devise a little bit thicker wrapper around a couple of pieces, but it's pretty darn close. When we talk later in the course and we start talking about the Android binder framework and the Android interface definition language, AIDL, you'll see how you can implement the full-blown active object pattern as a variant of the so-called broker pattern. And we'll talk about all that stuff probably maybe starting next week, maybe starting the week after. Okay, so the first thing you need to do from an implementation point of view is you need to implement the invocation infrastructure. Now keep in mind what we're trying to do here. We're trying to come up with a way to convert a method call from the client, say from an activity or whatever, some client thread or somebody who's making a call, into a method request or a message. And that thing is then going to be stuck onto a queue or an activation list. So that's what the proxy's role is. So the proxy is basically this surrogate that looks like the actual target of the request, but instead is just doing some minimal work to convert a method call into something that can be queued for later processing. Now, when we talk about more complex environments, when we talk about communicating between address spaces on an Android device, when we talk about communicating between an Android device and a server in the cloud or a data center somewhere, we'll see how proxy plays another very important role. So we'll talk more about proxy later. If you don't have the deep, fullest understanding of proxy, don't despair. We'll cover this as its own pattern later. That pattern appears in the Gang of Four book. It also appears in the POSA 1 book. You can look it up online. So that's basically what the proxy is. Oh, and actually, let me do something here. Probably want to clone that slide and add proxy URL. So if you take a look online, you'll find the proxy pattern is described on Wikipedia, so you can find what it looks like. Okay, so that's basically what the proxy is. If you take a look at the handler.java file, you'll see it defines proxies in the form of these methods called send method or message. So there's a couple variations. There's send message. As you can see, send message turns around and calls send message delayed. Send message delayed turns around and calls send message at time. And send message at time actually does something. And what that something is it basically converts things into a message that's going to be stuck into a message queue. So that's the way that the proxy works in this variant of the pattern applied to Android. It's a very simple kind of stripped down version. The proxy and method request implementation for the Android handler are not as sophisticated as the full-blown pattern, but they're good enough for our purposes to make the point. So the message gets turned into something that gets stuck into a queue. Okay, the next thing you need to do is you need to implement the activation list. The activation list is the thing that keeps track of these method requests, which, remember, a method request is an objectification of a method call. So it's going to basically store the information dealing with the parameters and other information that's necessary to identify what method was invoked. And so you need to be able to have some way to be able to insert and remove these method requests into some kind of data structure, which in this case is called an activation list in the pattern nomenclature. Typically, not always, but typically this list is implemented as some kind of synchronized buffer where you can have one thread or more than one thread putting requests, method requests into the buffer simultaneously in a synchronized thread-safe way, and then one or more threads taking things out of that buffer in a synchronized and thread-safe way. So what would that kind of thing look like in Android? Well, that kind of thing in Android would be something like the message queue. The message queue is defined as part of the core kind of OS framework portion of the Android middleware. And it has methods like enqueueMessage, which you give a message at a time when you want the message to run. And then it also has ways of dequeuing things from the message queue using methods like next, which will block. Then we have to go ahead and implement a scheduler of some kind. So in this particular case, and you can look at the scheduler a couple different ways, but in the context of the pattern, the scheduler is basically a so-called command processor. And let's see, I guess to be fully pattern compliant and cross-reference enabled, I should mention command processor processor pattern URL here. So the command processor pattern is a pattern, which we'll talk about later, which you can use to pass command objects between address spaces or between threads of control. And so the scheduler basically implements this pattern, and you enqueue things into the message, the activation list, and then you get it out in another thread of control. And the scheduler figures out when it can retrieve the request from the activation list. And there's a bunch of different variants. The simple one is just to have the activation list be a FIFO queue and have the scheduler simply do FIFO scheduling. Whatever's next in the queue, you take it out. There are all kinds of other variants. You could have a priority queue. That was the example I gave where Bill Clinton wants to order a Big Mac or a Wendy's hamburger. So we prioritize, presidents get special preference over other people. You might also have a situation where you're going to queue things up based on delays. So things don't get queued until a certain amount of time passes. So you might invoke a bunch of operations but give them different delays, and then they'll show up coming out of the queue in the order of their earliest deadline first in the queue. And there's other variants as well. You could have more complicated synchronization guards, where you could check to see if certain conditions were satisfied, and if so, then the scheduler would get a chance to execute or dequeue those method requests. In the Android case, it's pretty simple. We have this message queue, and things get queued up based on the order that they appear and or the time at which they're supposed to run. And so it's basically a timed delay, time-based queue. And so basically there's the looper, and the looper sits there waiting to pull stuff out of the queue, and it pulls stuff out of the queue, and then it goes ahead and dispatches it. So that's the scheduler. And then we have the servant. The servant's actually the guy who does the work, who implements the application-specific behavior when it receives work from a client. In general, servants can be implemented all kinds of different ways. One very common way to implement the active object pattern is to have the proxy and the servant have the same methods with the same signatures. And that way, it looks just like an object. You know, when you invoke a method on an object, the implementation of that method is the same name. It's got the same signature, the same parameters, and so on. In fact, it's typically the same thing. In an active object environment, you have a couple of choices. One choice you can make is to have there be a mirrored relationship between the name of the method you invoke and the name on the servant that gets called back. Another approach, which is more the way Android does it, is we have a method we use to pass the request there called sendMessage, and then we have a method with a slightly different name called handleMessage that actually retrieves the request and processes it. Probably the most obvious reason for doing that is if they called both methods sendMethod or sendMessage, you'd have an overload ambiguity problem, because handler needs to support both these things. It needs to be able to support sendMessage to get the data to the handler, and it has to have some kind of callback hook to do the work. So that's probably why they did it that way. But there are other alternatives. So in the case of Android, handleMessage is the thing that actually does the work. It's the servant, and you implement it by subclassing from handler and filling in whatever you want. So here we have a worker handler with a handleMessage method that does something or other. And then the last thing you have to do is figure out how you're going to get the results, if any, back to the original client who invoked the operation. Now, a lot of times with Android, when you do a send message call on a handler, you're not really expecting anything back in return. For example, imagine you have some long-running computation that's downloading a file in a background thread. And when that background thread is done, it wants to send the result back to the UI thread. Well, in that case, all it does is it simply says send message, and then voila, handleMessage gets called back in the UI thread, and the UI thread does something to display the result. So in that case, there really is no communication. It's just a one-way invocation. There are other scenarios, and we'll look at some in a second, where there's two-way communication. And so if there's two-way communication, you have to have a way to get back to your original caller. And there's a whole bunch of different ways to do this. One way to do this, which we show here in Android, is to pass as part of the original message to the active object, to the handler. You contain in the message essentially the reply handler, the handler of the guy who sent the thing in the first place. So you can see here, in this particular example, which we'll look at in more detail later, we get the message, we go ahead and we crack it open, and we get some arguments that were passed in. And then we go take a look at the args.handler field, and that's the handler of the guy who sent us the message in the first place. And we use obtain message, which is a factory method that's used to get back a message. And then we go ahead and fill in some results, and then we say reply.send to target. And send to target is simply a little convenience method that says send message this. It basically sends a message back to itself. So this guy is going to be used to send a message back to the original client. And I'll show you this in a second to make it a little bit more clear. OK, so that's kind of the implementation steps. Now what I'm going to do is I'm going to show you a really cool place in Android that implements this. And we're going to look at this example later on in the class, and you may get a chance to play around with it and use it for one of the assignments. But for right now, I'll kind of show you how it works under the hood. It's really cool. So there's something in Android that's called an async query handler. And async query handler is used in just a few places in Android, but one of the places it's used is in the MMS implementation for various things. Asynchronous query handler is a little helper class that is used to invoke calls on content resolvers, which I'll talk more about in a second, in such a way that they don't block synchronously for the content resolution operation to complete. So what is a content resolver? Does anybody remember what a content resolver is? Chad?
It handles the response from the content provider.
Right. And what's a content provider?
A way of sharing information.
Right. So the content provider is basically a facade or a proxy to data that's often stored persistently, most commonly using SQL-Lite database implementations. You can use other things too. You can use files and so on. But it's basically a way of getting access to some persistent data. And out of the box, if you use the content resolver, you'll do the following. You'll have an activity, and you'll call an operation like, say, query. There's other operations too, insert, delete, and so on. But you can call query on a content resolver. And by default, the content resolver will go out and get the data and return it back to the caller, but the caller thread blocks until the call returns. So that's what's called a synchronous two-way operation. Now, as you may imagine, there's all kinds of downsides. What's one of the main downsides with this in the context of Android?
You can't do anything with UI.
The UI thread will be blocked while this is taking place. And if you're doing a very complicated query, then you could end up with the dreaded application not responding dialog popping up, and you'll have problems, right? So what async query handler does is it implements the active object, and it actually implements the full-blown active object, well, a pretty full-blown active object here, in order to be able to decouple the invocation from the processing from the reply. And here's essentially how this works. So the activity invokes an operation on a subclass of async handler called myAsyncHandler, which you would create. We'll talk about why you do that in a second. You do that so you can get the results of the operations when they're done. And you do an operation with a name start, like start query, start insert, start delete, and so on. And start goes ahead and kicks things off, but it returns right away. It doesn't block. It's an async. It starts things off and returns immediately. And what happens is that the start query method creates a message, and it does a send message to a worker thread. It's a worker handler that's running in the background. So it's a background thread that's started up when the whole thing starts, and it continuously runs. And the send message call also returns right away, but the first thing it does is it converts the arguments into a method request or a message, sticks them onto the worker handler's message queue or activation list, returns right away, so that doesn't block. And then the worker handler's handle message call gets invoked in a separate thread of control, and that guy goes off and he does a blocking call on the content resolver. So the original activity thread is off doing whatever the activity thread wants to do at this point, waiting for more input from users. And there's work taking place in the background in a background thread in the worker thread, and that guy's querying the actual content resolver, and he's blocking, but he can afford to block because he's not blocking the UI thread. So that's perfectly kosher to do that. When the handle message in the worker thread returns, when the query operation in the handle worker thread returns, that guy then turns around and does a send to target call on the actual reply handler that corresponds back to this thing that was originally used to invoke the operation in the first place, my async query handler. And that asynchronously sends the result back and returns right away, so he can process other requests. And then this guy's handle message method gets called, and he turns around and dispatches the callback hook that is defined as an abstract method in async query handler that does the completion processing. So when you invoke, say, an async query, when the query is done, you get the result of that async query, which typically can come back to you as a cursor, which has the data that was requested that match your query. That comes back as a cursor back in the activity thread or the invoker thread, and that comes back with a onQuery complete callback hook. And so onQuery complete is an abstract method defined in abstract query handler. You subclass that, fill it in, and that guy gets called back after the query has returned asynchronously. So you can kind of see it's a really nice example of the active object pattern because we're decoupling the invocation of an operation, in other words, run a query, from the processing of that operation, and then we get the result back at some later time through a callback. In this case, it's a callback on a future that was dispatched. Really, really, really cool stuff. The query handler stuff is described here. Oh, and I guess I should also probably add path name for async query handler.java. So you can look at the code. It's really cool to watch how it all works. And if you don't know the active object pattern, and you don't understand all the things we just talked about, it's a little bit difficult to figure out what the code is doing. Once you understand the pattern, it's just a breeze. You're like, oh yeah, that's this piece, that's the proxy, that's the scheduler, that's the activation list. And what makes it tricky, of course, is that these things appear in multiple places, right? It's not self-contained. The async query handler file has some pieces of it. The looper and handler parts of Android have some other pieces of it. But the pattern is what pulls all this stuff together, and knowledge of how that pattern works helps make it a lot easier to understand how to use this particular mechanism. I remember over the summer we were doing a project with some folks here, and we were trying to decide, do we use async query handler, do we use cursor loaders, and I think one of the things that made async query handler hard at the time was just not really knowing how all the pieces fit together, right? And so once you know the pattern, it makes it a lot easier. Okay. Internally, the async query handler uses a subset of the active object pattern. So as you can see, we start the query. That turns into creates a message. We call the worker handler thread send message call. That goes over here to the worker handler object and its thread through its handler. And this guy has a looper, and he pulls the requests off, does some processing, and then they get called back, and so on. And there's more parts to it than I'm showing you here, but these are the basic pieces. There's the source code. I can get rid of that comment over here. We actually don't need to do that. Let's see if there's anything else we need to cover there. So anyway, it's definitely worthwhile to take a look at that code and sort of puzzle through it. Once you understand the pattern, all the pieces make a lot more sense. And you find this through and throughout Android, through and throughout Java. The people who implemented Java, the people who implemented Android really understand patterns, and so you'll see a lot of recurring approaches over and over and over again. And it's almost, paint by number after a while. There's certain other idioms we'll talk about later when we talk about services that use command processor pattern, and they do the same thing every time. Okay, so let's talk a bit about the consequences of this pattern. So the good part about this pattern is it enhances concurrency and simplifies synchronization complexity. And the reason it enhances this stuff is because it allows us to be able to have client threads and method invocations run concurrently. You invoke an operation and it runs in another thread. Multiple threads can invoke operations. They'll run in the other thread or threads, as we'll see in a second. You can have a scheduler that can be used to evaluate various synchronization constraints. If you have multi-core processors on your platform and you have the stomach to make sure that your servant code is thread safe, then you can actually spawn a pool of threads, typically roughly around the same size as the number of cores, give or take. Typically you have a few more threads than there are cores. Maybe if you have 4 cores, you might have 8 threads in the pool for various reasons. And so in that case, when you invoke these operations, you could have multiple threads or one thread invoking multiple operations, and all of these operations will now run concurrently. So you can transparently speed your program up, assuming A, that there's work that can be parallelized, which is always tricky, and that you've done a proper job of doing locking and other things in your code. And once you understand monitor objects, once you understand the basics of synchronization with Java, that becomes tractable, certainly. Another interesting thing here is that the method invocation order and the method execution order can differ. Now, this is true of the pattern in general, but in the case of Android, if you put delay operations, if you take a look here, you can see we have these delay calls. When you invoke a message, you can give it a delay time. You can either give it an absolute time, or you can give it a time that's relative to the current time of day. There are different method calls for each one of those things. And that will affect where the method goes and when it gets run. And so they store things in a way so that they're queued up and run at the right time, at the appropriate time. There are, of course, there's very rarely there's a totally free lunch in software design. So there are some liabilities or downsides to this particular pattern. So one of the things you got to be very careful of is that you don't end up running into additional overhead for all the different parts that are needed to make the active object work properly. And let's talk about where those overheads come from. So one of the things you got to do when you do active object is you typically have to allocate the memory dynamically, because the thread that invokes something is different from the thread that executes it, and therefore you have to typically have to allocate it dynamically because they can't share buffers easily. And the minute you start allocating things dynamically, there's a bunch of issues. The code may be somewhat slower because you have to allocate stuff and go out to a heap. You typically have to acquire a lock to lock the heap. And in languages like C++ and C, where you don't have garbage collection, you have to deallocate stuff, and that requires things, and it does heap memory. There's all kinds of stuff that is potentially a downside if you allocate memory dynamically. In Java, you don't have a lot of choice most of the time, but in other languages you do. Another consequence is whenever you put these things on and off the queue, that involves synchronization operations. And synchronization operations are pretty fast, but they're not completely free. Nowadays, good synchronization operations that are implemented in hardware are probably running at the order of nanoseconds or tens of nanoseconds or maybe microsecond or something like that. They're really fast, but it's more than nothing. The real kicker is the context switches. When you start moving things between threads or between processors or cores on a machine, then it typically takes a while to switch context. And that can start running in thousands of instructions to do that. There may be tens or hundreds of microseconds of overhead for context switches. We're getting faster and faster all the time, but it's still not for free. And another tricky thing, if you start running in multi-core environments or shared memory environments where you move data between different processors, that can involve various low-level CPU cache overhead, from flushing caches and dealing with cache lines and all kinds of things. That's kind of a hidden overhead because it doesn't really show up at the software level, but it's all part of what the underlying bus and memory hierarchy and memory system is doing to actually implement this stuff down in the hardware. So those are some things that can make the overhead be more than would be the case to just make a normal method call. Now, when would this matter? When would this not matter? If you're going to run an operation that runs for a long time, you're going to invoke an active object method that's going to run for a minute, the fact that it took a couple of microseconds to switch context and synchronize and allocate memory is completely in the noise. If you're going to run an operation that adds two numbers together and returns them, these overheads really start to add up. So think carefully about how long your operations run before you decide to use active object. Don't just go crazy and put active object everywhere, because it'll guarantee to slow your system down. Another tricky thing is, and this is almost always a liability when you're starting to deal with concurrency, just about anything you do that runs concurrently is going to be tricky to debug because you've got multiple things going on. Those challenges we talked about before, the accidental complexities, crummy debuggers, changing in terms of the order in which things run, changing the time duration over which things run. Those are all real subtle and tricky issues. And so there's non-determinism issues. Your program may not always execute the same each time you run it, so debugging can be more difficult. That's just a problem in general. People sometimes use subsets of active objects to make this more tractable. A very common subset of active object is to kind of simplify the proxy, kind of simplify the servant, and kind of pass messages back and forth using queues. If you think about what I showed you with Android, it's kind of somewhere in between. It's not the full-blown active object, but it's not just a message queue either. It's got some additional flair on either side of that. So it works more sophisticated. But it's certainly an example, a nice example of active objects. There's lots of known uses of this stuff. There's a bunch of programming languages that are based on the so-called actor model, which is a mathematical model of computation, concurrent computation. And it basically does what we just talked about. If you read the Wikipedia link about the actor model, it sounds like the active object pattern. No surprise, it's basically the same thing. There are active object implementations in various languages and frameworks. Here's a nice example that Herb Sutter from Microsoft did, showing how to do a simple active object implementation in C++11. I won't go through this, in the interest of time, I won't go through this in full-blown detail, but it's really cool. It basically type-defs a functor with a operator function call method defined in it, and you go down here, and in the constructor of this active class, it goes ahead and creates a new thread with an anonymous lambda expression that will run in a separate thread of control, calling the run method. Here's the run method. The run method loops while we're not done, and it pulls messages off of this message queue, and it goes ahead and executes those messages because they have a functor defined on them. And when the destructor runs, it says shut yourself down. So anyway, I won't go through the whole thing in here, but it's pretty cool, and it illustrates how to implement this stuff in C++11. ACE, the framework that we've developed for many years here at Vanderbilt and other places, also has active object implementations, so you can learn more about those as well. So to summarize, clients may sometimes need to be able to issue service requests that need to run in other threads of control. And in that case, we may want to schedule the activities to run or schedule the operations, the request to run based on various criteria, such as the time or the priority or the deadlines and so on. The active object pattern kind of coordinates all this stuff and makes it easier to program, so it looks more like a regular programming object. It just happens to run concurrently. And you can read more about it here. And as I mentioned before, it's instructive to compare and contrast active object with monitor object. The main difference is active object is more powerful. It can run things more concurrently, but it also is more complicated, and there could be some additional overhead for the reasons we talked about before. Okay. Any questions about any of the topics that we just covered?